Hello and welcome to another episode of Research Talk. Today we have with us Pritesh Keshari from Mirzapur, Uttar Pradesh. He completed his BSc from Zakir Hussain Delhi College and MSc from IIT BHU, and currently is working as a research scholar at IISc Bangalore. His research focuses on a sustainable chemistry using earth abundant transition metal in water, and today he will present his own work, a sustainable approach for carrying out reaction in water using non-ionic based surfactant. His research work also has been featured in the Times of India, the New Indian Express, and the Chemical Today magazine, highlighting its impact and relevance in the sustainable chemistry. So, Pritesh, welcome to the talk, and the screen is yours.
Thank you, Max, for your kind introduction. Good evening to all. Today, I will discuss with you a research work which is published by me in 2024. The title of the paper is Micelles enabled nickel-catalyzed P-Arylation of aromatic phosphine oxide in water under mild condition. So, as a chemist, we synthesize a number of molecules in our laboratory as well as pharmaceutical drugs. As per the Asian Green Chemistry Institute, approximately 80% waste contribution in a pharmaceutical company is coming from this organic solvent, and this organic solvent help us to drive the organic reaction. But at the same time, this organic solvent is not cleaner with us. It had inherent problem associated with it, such as carcinogenic toxicity as well as flammability. So to synthesize their pharmaceutical drugs in at industrial level, they recently industry are looking for the cleaner way to synthesize their drugs unit. Some of the well-known companies such as Takeda and Novartis recently they are moving towards the sustainable synthesis of their drugs unit. So one example I have here mentioned such as TAG 954. It's synthesized in a greener solvent as compared to what the previously known using organic solvent their synthesis, as well as their yield is also good as compared to the previously reported. Now, I have listed here some of the commonly solvent which are generally used by the organic chemistry to carry out the organic reaction. If you able to see that the highlighted portion of this table is clearly indicate that we need to substitute some of the solvents such as DMF, DMAC, and MP. Recently, DMF is banned by the European Commission, and this is highly carcinogenic. So, in order to search alternative, some of the group already find the alternative of this one, such as Lipsutz research group as well as Honda research group. They try to design some of the non-ionic surfactant, and when this non-ionic surfactant is dissolved in water, simple water, it form myself, and this myself it's not only help to carry out the reaction but at the same time able to enhance the reaction rate, which I will discuss with you in a coming slide. Now a question may become in your mind that this solvent can this all organic reaction can be carried out in simple water. The answer is obviously, yes, but at the same time, we all know that from our basic knowledge that like dissolve in light. So, maximum organic molecules are lipophilic in nature. They might face the problem of solubility in simple water. So, when a substance is not soluble in that solvent medium, they might face the problem of mass transfer, energy transfer during the chemical reaction. So, we can't go directly with the water for the onic reagent, which is highly moisture and air sensitive. So to search the alternative of this onic solvent and keeping in mind of the 12 principle of a green chemistry, various research group designing a non-ionic surfactant. So this non-ionic surfactant at the same time help us to act as a ligand, solvent, as well as reaction promoter. Now, I will discuss with you little bit about the introduction of a micelle. What is generally micelle? Micelle is basically the amphiphilic molecules which have both hydrophobic tail and hydrophilic head. These amplific molecules, when dissolved in water, it self-aggregate to give the micelle, which is either in a spherical phase, cylindrical. There are various morphology of this micelle is there. So we have generally classified this surfactant into broadly two categories. One is ionic and another one is non-ionic surfactant. The simple example of this one you can see in case of what the detergent we are using in our home. It is fully working on the same principle. So ionic surfactant in the sense that it have some charge species on their hydrophilic head, and non-ionic surfactant is that this do not contain any charge on the hydrophilic head of their solution, of their micellar solution. So basically this micellar catalysis contributes significantly to carry out the reaction in water, but at the same time it also provides the medium to solubilize the highly lipophilic onyx reagent or a substrate. At the same time, this since all these onyx reagent and substrate go inside their hydrophobic core, so it able to give the close proximity as well as reduce the degree of freedom of that substrate to give for better reaction. Now, coming to the my approach which I utilize in our research paper to synthesize a new non-ionic surfactant which is derived from the agricultural waste. We know that India is the second largest producer of cashew nut shell, since the cashew nut have a two portion, one is called the cashew nut and another one is called the cashew apple. This cashew apple basically act as a wastage for us. So we accept this as a wastage, as an opportunity to convert into our solvent system. So what we have done, we derive this agricultural waste which contain this long chain hydrophobic and long chain hydrophobic as well as phenolic unity. With the help of ethyl bromoacetate, we attach this on the phenolic unit and bring the hydrophilic impact unit. So it's able to give this kind of white solid non-ionic surfactant, which we given the name CNSL 1000. And this 1000 is coming from the hydrophilic portion of this hydrophilic unit. So when we dissolve this hold the compound in a water, it self-assembles like a micelle, which consists inside the hydrophobic core and outside the hydrophilic. Since we converted the agricultural waste into a solvent system, which help us to carry out the reaction. For the practical purpose, here we saw a simple Chamberlain-like coupling of a secondary phosphine oxide with boronic acid in the presence of earth-abundant nickel metal, which is more sustainable as compared to their analog like palladium to obtain the tertiary phosphine oxide. Since the synthesis, the CP bond forming reaction was discovered by the Hirayan co-worker group using the first time using palladium metal. So nickel is more sustainable compared to their higher analog for TR5D metal species. So we take the challenges to carry out this kind of reaction in simple water which act as a bulk phase. Now, some of the application of this phosphine oxide is mentioned here, since this phosphine oxide such as pineapple used for the asymmetric catalysis and as also act as a folate synthesis of folate host material and some anti-cancer drugs. Since when we synthesize the phosphine oxide, we can easily reduce this phosphine oxide to the phosphine, and which also act as a ligand for carry out the cross-coupling reaction. Now, since we know that ligand play a crucial role in tuning the property of a metal species, so during the optimization purpose, I screened a number of ligands and found that ligand alpha able to give better conversion as compared to the all other ligand. So we are just curious to know that what is the difference between L4 and L5 here. So since L4 and L5 both have a same chelating site, but the difference is here that L5 ligand have greater hydrophobicity due to attachment of this tertiary methyl group here. Butyl group is here. So for this, in order to confirm it, we carried out the DLS study. So we found that when this nickel acetate form a complex with bipyridine system that the ligand L4, it able to give the average size of aggregate around 203 nanometer. But when we carried out the same complexation in our surfactant CNSL 1000 and surfactant aqueous solution CNSL 1000 and with this 4,4 diethyl butyl bipyridine ligand, we able to achieve the average size of aggregate is in two regions. One is 462 and another one is 2183. It clearly indicate that greater the hydrophobicity of ligand, it will better go inside the hydrophobic core of the micelle. Now, we this is our the standard condition under which we carry out this reaction. If you clearly see that entry 8 and entry 9, in case of organic solvents such as TMF and 1,4-dioxane, our reaction in the standard condition it able to not give a better conversion as what it is giving in case of our surfactant solution. So through this, we can say that organic reaction can be carried out in a better way using the concept of a micellar catalysis. Now, in order to know the fate of nickel species present in our system, we carry out the XPS analysis. From the XPS, we found that the nickel is present in the plus two state, as well as to show the practical utility of our method, we carried out the gram scale synthesis of tertiary phosphine oxide. At the same time, we also done the in situ recyclability study. From the in situ recyclability study, we observed that our nickel catalyst is active up to the fourth cycle, but their conversion is going down because due to accumulation of a phosphine oxide, this which bind with the nickel species present in the system inhibit the further reaction. So it able to give influx recyclability up to the fourth cycle. Now, in before proposing the reaction mechanism, how it proceed this reaction, some control experiment was carried out using 3-fluorophenylboronic acid in the presence of our complex and surfactant solution. We observed the multiple peak in the 19F NMR analysis as well as 31P NMR analysis of a crude reaction mixture. And this intermediate species is detected when we carry out the high resolution mass spectroscope species and their masses matches with this kind of intermediate which confirmed from the HRMS study. So on this basis, we propose our reaction mechanism. From this, we observe that the intermediate first species first undergo simple nucleophilic addition reaction, and this secondary phosphine oxide is generally under the equilibrium with their ketoenol form in the presence of a base. It go for the nucleophilic substitution reaction and to form the intermediate two species, and these intermediate two species undergo transmetallation in the presence of phenylboronic acid and triethylamine to direct this unit to here. And this unit went for the reductive elimination to obtain the tertiary phosphine oxide as and given nickel 0. And since we carry out the reaction in a simple air atmosphere, it oxidized to the nickel 2 in the presence of air. So this is the way through which we achieve our whole catalytic cycle. Now, coming to the conclusion portion of my talk is that we take the advantage of this agricultural waste to convert into a non-ionic surfactant. When this non-ionic surfactant is dissolved in a water, it able to give a solvent system which is useful to carry out the different kind of reaction. Here I have shown only one kind of reaction, that is CP bond forming reaction. At the same time, it is basically a green enabler for carrying out the nickel-catalyzed CP cross-coupling reaction, and it is operated under the mild condition because the temperature range is 60 to 65 degrees centigrade only. So through this, I just want to conclude my word. Thank you for listening.
Nice work and nice presentation, Pritesh.
If you enjoyed this session, don't forget to like, share, and subscribe. We'll meet you in the next episode, next session. Thanks for watching.